Thank you very much, and it's wonderful to see such a full house here this evening. So yes, this is the end of everything. Probably the most depressing talk you're going to have this year. It's about what's going to happen to the Earth, the Sun, the galaxy, and the universe in due course. We're going to be going through future years. We're not jumping to the end straight away. We're going to be looking at what's going to happen in a few thousand years, a few tens of thousands, hundreds of thousands, millions of years, working our way up to the end of everything. So it's a bit like to eternity and beyond, if you want to think of it that way. That's what we're doing. So I'll be giving a little bit of a preamble and then talking about the future of the Earth and the Sun and the solar system, then looking further into the future for stars and galaxies, and ultimately the far, 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 far future and the ultimate fate of the universe. And then I'll sum up. If you're thoroughly depressed by this point, I'll try and sum up and just put a slightly more cheery note on it, so you don't all leave with your heads low looking down at your feet. So yes, February 2020 it was, according to this date, that I gave you the beginning of everything. I gave it a long, long, long time ago, but I gave it a refresh and gave it again in February of 2020. I'm not going to go through it again, but for those who've forgotten what happened 3 years ago, I said that the universe was made something like 13.8 billion years ago. In the very early part of the universe, it was about the size of a golf ball. What we now consider to be the entire observable universe used to be a lot smaller, and you could fit it inside a golf ball. The universe made lots of protons and neutrons, which eventually became lots of hydrogen and helium. And it took about 3 minutes for that to happen. So the universe made all of the hydrogen that we're talking about in 3 minutes, and ever since then, the universe has simply been shuffling that hydrogen around. Some stars have been converting hydrogen into helium and carbon and nitrogen and oxygen, and us, eventually. But basically, that's what happened in the very early universe. For this talk, I'm talking about what's happening from now onward. We're starting from, let's assume we have a universe full of galaxies and stars and planets. What's going to happen next? And to help you keep track of where we are, because I'm going to throw huge numbers of numbers at you in terms of thousands of years, millions of years, billions of years into the future, there's a timeline along the top here, and that will hopefully help you keep track of where we are. Each box at the top there means 10 times further into the future, because we can't have a linear scale because that's just crazy, so it's a logarithmic scale. So what I mean is, if we start with now, we're talking about 10 years into the future, 100 years into the future, 10 to the power 3, 1 with 3 zeros, 1,000 years into the future, 10 to the 4, 5, 6, a million years into the future, 7, 8, 9, a billion years into the future, 10, 11, 12, a trillion years into the future. So this red box is going to be there for basically the rest of the talk, and we'll go along that scale just to remind you where we are in terms of how far into the future we are talking. And I must give credit to this particular paper published by Adams and Laughlin quite a few years ago, but they calculated the timescales on which various astrophysical phenomena are likely to happen. And that helped me get my slides in order, because I wanted to say this, 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 and this, but I also want them to be in time order, not necessarily in logic order. So I used that particular paper to try and get my slides and all my ducks in a row. So I'm not going to talk about 10 years or 100 years. I'm going to jump straight to 1,000 years. Let's assume we don't blow ourselves up. Let's assume we get climate change under control. The next interesting thing, as far as I'm concerned, is when we think about the rotation of the Earth, in 1,000 years, things will be a little bit different. In a separate talk, which I called Just a Second, we saw that leap seconds get added every few years to try and keep the rotation of the Earth in sync with our clocks. But the Earth is slowing down because the moon is a sort of a brake on the spin of the Earth. So instead of leap seconds being added every few years, in 1,000 years, leap seconds will have to be added every few weeks to try and keep our clocks synchronized. That's something that we can predict quite well because we understand to some extent the long-term change in the Earth's rotation. There are quite a lot of things which we really can't predict. Although we think some stars are going to go supernova in the next few hundred, few thousand, perhaps longer, perhaps even a few million years, we can't predict when that's going to happen. So maybe Antares might go supernova in 10 to the 4 years, 10,000 years. It's only a guess, though, and we really can't say. But there are things that we can say with much greater precision. For instance, we know the precession of the Earth. We know that the Earth's axis points to a particular point in the sky, and that changes over a cycle of 26,000 years, the precession of the Earth's axis. And we can look back in history to tell that's what's happened, and we can look, for instance, at what did people consider to be the pole star thousands of years ago, and hence we know it's not the same as the pole star we talk about today. So at the moment, the pole star is Polaris. That's the closest star to where the pole is pointing. But as the Earth's axis precesses, it traces a large circle on the sky, and in a few thousand years, the pole will be pointing towards not quite Vega, but very close to Vega. So the pole star, at long last, will be one of the brightest stars in the sky, which a lot of people assume it is already. So that's going to make life really easy for Boy Scouts when they're told to get your badge, you have to be able to point out the pole star. But are there any other consequences of having the pole star change? Well, at the moment, the Earth is closest to the sun in January when the northern hemisphere is experiencing winter because the Earth's axis is pointing away from the sun. But if instead of pointing at Polaris, it points at Vega, that means the Earth will be closest to the sun when the northern hemisphere has its summer rather than has its winter, which means we are going to be closer to the sun and tilted towards the sun, which means seasons are going to become a little more sort of dramatic, if you like. Summers are going to be hotter, winters are going to be colder. Regardless of any other changes to the Earth's climate, simply changing the axis of the pole is going to change our climate. And variations in the Earth's climate because of the spin of the Earth or because of the orbit of the Earth around the sun, collectively, these changes that are a function of astronomical changes to orbit and spin, these are called Milankovitch cycles. You can go away and look that up if you want to know more about them. So we know this is going to happen, and we know precisely on what timescales this is going to happen. On a slightly longer timescale, we've now gone 10 to the 5 years into the future, 100,000 years into the future. The Voyagers, by this point, will have passed some nearby stars. So the Voyagers, remember, were launched in the 70s and then went past Jupiter and Saturn, and in the case of Voyager 2, Uranus and Neptune as well, and since then have been flying out of the solar system. Voyager 1 is heading off in a direction such that in 10 to 100,000 years or so, it's going to go past the star system Gliese 445. And Voyager 2, heading out in a different direction of the solar system, is going to pass the star Ross 248. We've got no idea if they're inhabited by any planets with interesting beings going around them, but Voyagers are going to go sailing through those solar systems on this timescale. Pioneer 10 and Pioneer 11 were launched earlier by a few years, but because of the way they were given a gravitational assist, they're going a little more slowly, and so it'll take them longer to get to the nearby stars. Pioneer 10 is heading off in the direction of Aldebaran. Pioneer 11 is heading off in the direction of the center of the galaxy. On this same timescale of 100,000 years into the future, that's the timescale over which ice ages come and go for the Earth. So that, according to the historical records, which we can find by looking at geological records, we know that the Earth has gone through repeating cycles of ice ages and so-called interglacials, the periods in between ice ages where the Earth warms up a bit. And we know these tend to repeat on timescales of order 100,000 years. We've entered into an interglacial not that long ago, which means the next ice age is due in about 100,000 years. So 10 to the 5 is, roughly speaking, the timescale on which we can expect the Earth to go through its next ice age. And that is yet another manifestation of these so-called Milankovitch cycles, changes, very slow changes to the spin and the orbit of the Earth. 10 to the 5 years into the future, the Earth is still slowing down because of the effects of the moon. And now it's got to the point where leap seconds would need to be added not every few years, not every few weeks, but we would have to add a leap second every day to keep the clocks synchronized with the rotation of the Earth. So in other words, we would have to standardize that the day is not 24 hours long, the day is 24 hours and a second. And we would have to insert that extra second basically every day. When we would insert it Would it be midnight? Well, if midnight, midnight where? Midnight at Greenwich? Midnight in New York? Midnight in Japan? Well, if we all disagree, then all our clocks will be out of sync. So it's a little bit of a problem, which is something I covered in that particular talk. But it's just going to continue to get worse and worse and worse as time goes forward. On a timescale of 10 to the 5, we can expect a few of our neighboring stars to have gone supernova by now. We don't know if it's going to be Antares that goes first, or Betelgeuse that goes first, or possibly Eta Carinae that goes first. This one has already started shedding a lot of its outer atmosphere. This star looks extremely unstable, so perhaps this would be the first one to go. This enterprising astrophotographer in Prague took this image of the night sky in front of Prague, an observatory in Prague, and he's taken a very nice image, but he's decided to change Betelgeuse and actually just make it look as if Betelgeuse goes supernova, that's what Orion is going to look like. In other words, we can just about see the belt of Orion and Rigel, and Betelgeuse has been replaced by this very bright object, which will be brighter than the full moon and probably visible during daylight. So again, we don't know when this is going to happen, but it's going to happen sooner or later. But it's not only supernova we have to worry about in terms of, well, Betelgeuse is a few hundred light years away, maybe that's not too much of a problem. There are various rather unstable stars called Wolf-Rayet stars. And Wolf-Rayet 104 is 7,000 light years away, which sounds like an enormous distance. Even if it decided to explode, surely that's not going to be a threat to Earth. Well, it might be, because some objects, when they die, emit more radiation than a supernova. This particular one has very pronounced jets. Rapid rotation of the Wolf-Rayet system produces jets heading off in different directions. And if we're unlucky enough to be in the line of sight of one of these jets, then the radiation from this star at the end of its life could, in principle, strip the Earth of its atmosphere, even at a distance of 7,000 light years. That shows you the enormous amount of energy that's coming out of these jets in these rapidly rotating systems. But hopefully that will only happen if the jet happens to line up with Earth. If the jet doesn't point towards Earth, we'll probably escape the death throes of that particular star. As stars go around the Milky Way rotates once every 100 million years or so. So on a time scale of 1 million years, different stars are rotating around the Milky Way, all in their own independent orbits, if they're not part of a multiple star system. So every once in a while, we are going to move around the Milky Way, and one of our neighbors might just happen to get a little bit closer as we go around the Milky Way. And one star, it is predicted, Gliese 710, is going to get very close to us. Gliese 710, for a little while, is going to come close to the solar system and then pass a little bit further away again. So it looks like a rather odd orbit. You have to remember that both stars are orbiting the center of the Milky Way. So Gliese 710 is actually going to come plowing into our Oort cloud without even asking first. It's going to come plowing in, and of course, it's going to disrupt the Oort cloud. The Oort cloud contains trillions of icy bodies, and we think that any object dropping in from the Oort cloud is what we now call a comet. And so as Gliese 10 comes into our Oort cloud, it is almost certainly going to disrupt the Oort cloud and produce loads of objects which come hurtling into the inner solar system. And it's predicted that it'll probably produce, for any planets in inner orbits, probably it'll produce naked eye comets, many per year, for 1 million years or so. So there's going to be an absolute rain of comets when this star passes by. And it's interesting to note that for a little while, there will actually be our sun and Gliese 710. There will actually be 2 suns in our solar system for a little while. I know you've seen that before, but it's not going to be quite like that. But it will be interesting to know that our solar system will actually have 2 suns for a while. We're still at 1 million years into the future. Perhaps you recognize Meteor Crater, Arizona. Does that mean we expect one of these impacts every 1 million years? No. The reason for showing this picture is twofold. One, when this asteroid struck, my God, we were lucky it didn't hit the visitor center. I mean, good grief. What a stroke of luck that was. But no, the 1 million years in this context is not how often we can expect this, but 1 million years is the time scale over which you would expect the evidence of a meteor impact to disappear. Because of weathering on Earth, This particular impact is, I think, tens of thousands of years old. If it was 10 million years old, we wouldn't see that crater because weathering processes on the Earth, geological processes, would eliminate any such evidence. Now, you might say, well, that's true on Earth, but it's not true, for instance, on the Moon, is it? Well, actually, yes, it is, because, for instance, the footprints on the Moon are not going to last forever. In a million years, those footprints will probably be gone, not because of weathering, but because the Moon is constantly bombarded with micrometeorites. And so, effectively, it's always churning up the soil because it's always being bombarded with small impacts. Even the Apollo landers, the lunar landers, the rovers, and all the other equipment they left, even that eventually will just disintegrate under the bombardment of radiation onto the Moon, mainly in the form of tiny physical particles. So although we tend to think of those footprints lasting a long time, only a million years or so, which on this scale, of course, is not that long. Pioneer is flying into the solar system, flying out of the solar system and probably passing other solar systems. It might take 10,000 years to reach the next star. So on a timescale of 10 to the 7, 10 million years, it will probably have passed quite a large number of solar systems. If left unperturbed, it might have already passed 1,000 solar systems by this particular point. So what is this particular point of 10 million years? It's the point at which this plaque will no longer be readable. There is a plaque on the side of Pioneer 10 and Pioneer 11. It's a aluminium plaque, but it will erode, it will corrode. It will effectively end up so pitted because of the impact with everything it hits on the way that it won't be readable. You tend to think of space as empty, but no, when you're flying through interstellar space, there is a certain amount of individual molecules, atoms and molecules, and most importantly, small particles of dust. And there aren't many of them, but in 10 million years, you will hit a lot of them. And so the plaque, which tells anybody that receives the Pioneer or catches the Pioneer, it tells them who we are, how big we are. A pulsar map tells them where we came from, and it says we came from the third rock from the sun. But after 10 million years, if nobody has caught Pioneer, by then, anybody that does catch it will not understand where it has come from because they will not be able to make sense of the plaque on the side of Pioneer 10. What about Saturn's rings? To think about the future of Saturn's rings, we have to have some idea of where Saturn's rings came from. So is it possible that a moon like Mimas actually made Saturn's rings? And anybody that looks at Mimas might think to themselves,
that's no moon, it's a space station.
Because it certainly does bear a striking resemblance to the Death Star. So does it mean that Mimas was actually hit by something and possibly disintegrated and then rebuilt itself? People have done simulations. There's the credit on the side there. A simulation. What if a moon like Mimas was pulverized by a passing comet or something like that and produced a whole load of debris? How long would it take to make the rings of Saturn? Notice the time scale. It doesn't take a long time to make a ring system. In other words, the pulverized rubble of the moon that was disintegrating doesn't take long to spread around the orbit. It only takes a matter of days or weeks or possibly months to make a ring system. As time goes by, all of these particles will slowly drift inwards due to a process I'm not going to describe, but basically all the particles in Saturn rings are slowly migrating inwards and eventually raining down onto the surface of Saturn. So from when they were made, they've ended up over millions of years drifting inwards into the rings we see today. But on timescales of many millions of years, let's say 10 to the 8, 100 million years into the future, these particles will continue to rain down on Saturn and the rings will disappear. So make the most of them while they're there for those that like imaging planets, because Saturn's rings will not be around forever. When it comes to trying to predict what else is going on in the solar system, not only the existence of Saturn's rings, but if you want to know where is Jupiter going to be in 10 to the 8, in 100 million years' time, the answer is we can't predict that, because ultimately the solar system is unpredictable. It's chaotic on those timescales. We like to think when we build ourselves an orrery or a tellurian, we tend to think, oh, this is a nice clockwork system. Isaac Newton would be proud of this. Basically, once the planets are in motion, if you know where the planet is and you know how fast it's moving, you can work out where it's going to be in a year's time, in 1,000 years' time, in 1,000,000 years' time. You can certainly dial the clock back and work out where were the planets, for instance, 2,000 years ago, if you wanted to work out what was going on with the Star of Bethlehem, but you can't dial the clock forward 10 to the 8 years and expect to know where all the objects are. Basically, on this time scale, the solar system is chaotic. We don't even know which planets will be in the solar system. It might be that Jupiter has decided to kick out one of the other planets. Much like there have been rearrangements in the past, maybe there will be a rearrangement in the future. So that's one thing to bear in mind. Prediction of what we think is easily predicted doesn't apply on timescales of many, many, many millions of years. One thing we are reasonably sure about is that the Milky Way rotates roughly once in 100 million years, maybe a couple of 100 million years. So again, on timescales like this, the Milky Way will have rotated approximately once. And what's going to happen is the sun, that's where you are there, you are here, so the sun is sitting at the moment in between two spiral arms of the galaxy, which means we're in an area which is not particularly densely populated. If you work out how many stars are around us, how many stars are within 10 light years of us, it's not as many as we would find if we were in a spiral arm. And as we go around the Milky Way, we are going to end up drifting into one of those spiral arms. So on a time scale of about 10 to the 8 or so, we are going to find ourselves in a spiral arm of the galaxy, surrounded by a lot more stars. The local density of stars in our neighborhood is going to go up quite substantially. So perhaps instead of our nearest star being 4 light years away, maybe our nearest star is only going to be a couple of light years away. And instead of having 100 stars in our neighborhood, maybe we're going to have many hundreds of stars in our neighborhood. So what's the consequence of being in a crowded part of the Milky Way? One of the consequences, like Gliese 710 coming our way, if we've got lots of neighbors, it's more likely that one star is going to pass close by, disturb our Oort cloud, and send loads of comets and asteroids coming our way. So the likelihood of an extinction level event is going to go up when we go into a spiral arm of a Milky Way. When we look at how many species have been extinguished as a function of time, going back the last 500 million years, we find every once in a while there's a spike where a whole load of species completely disappear from the fossil record, indicating some sort of disaster got rid of a lot of life on Earth. The last one was the so-called KT boundary, the boundary between the Cretaceous and the Tertiary periods. That's the one that killed the dinosaurs. So that was about 65 million years or so. But you can see the spikes aren't totally regular, but we get quite a few spikes roughly every 100 million years or so. And so on a time scale of 100 million years, when we next go into a spiral arm, we can expect another spike. We can expect another extinction level event. Again, we can't predict exactly, but we can see that they have happened, we can understand why they happen, and we are going to get another one on this sort of time scale. So this is, of course, just an artist's impression. A big lump of rock is almost certainly going to come our way on this sort of time scale. You can see what it's heading for. Italy is going to have a really bad day. But of course, anything that large, an extinction level event, is not going to be bad news for a city or a country. It is going to be bad news for the planet. Species will be exterminated if we get hit by a large enough piece of rock. The uncertainty, of course, is whether we are one of them or not. In principle, we might be able to survive. Mankind is where it is today, and of course, we have survived the last, I don't know how many, extinction level events. It killed the dinosaurs, some mammals survived, they ended up as us. So it will happen again, and we don't know whether or not that will be bad news for us or whether we're going to have to figure out how to deal with it. As well as being in a spiral arm, meaning more stars are likely to perturb the Oort cloud and send comets and asteroids our way, Another potential problem is we're going to have more neighbors. At the moment, the neighbors we've got, none of them are supernova candidates. All of the supernova candidates we know about are hundreds or thousands of light years away. None of the stars within a few tens of light years are the sort of stars that are massive enough to go supernova. But when we're in a spiral arm and we have 10 times as many neighbors, maybe we're going to get unlucky. Maybe one of our neighbors is going to go supernova when we're in a much denser part of the Milky Way. A supernova within 100 light years would definitely be a danger to Earth. If a supernova went off within 20 light years, it would probably end all life on Earth. It'll be even worse than an extinction level event from being hit by a large asteroid. And although that sounds a bit alarmist to say a supernova could go off relatively close to Earth, we have evidence that it's happened before. We have evidence that supernova, if they are close enough to Earth, will leave a particular iron isotope in the Earth's sediments. It'll rain down on the Earth and get incorporated into the sediments of Earth. There's a particular isotope called iron 60. It does not occur naturally. It is only made in supernova explosions. And the isotope changes. If you generate iron 60, after a few million years, it'll change into something else. It happens to change into cobalt and then nickel. So in other words, a supernova will generate iron 60, but it won't hang around for many, many, many millions of years. It certainly won't hang around for 1 billion years. And we have found iron 60 in the Earth's sediments, in the Earth's crust, effectively. So we know there must have been a supernova that went off not that far away, close enough to generate iron 60, which we've then found in the Earth's crust. It must have arrived relatively recently on a time scale of a fraction of 1 billion years, because it can't have been around since the Earth was formed, because it's radioactive and it would have decayed into something else by now. So we know that supernova have gone off locally, and if one goes off close enough in 100 million years or so, it could be really bad news. It could be literally life-ending. A picture you've seen 17 times already. The Earth is continuing to slow down. The Earth is spinning, and after 100 million years, the Moon is still slowing the Earth down. It is still robbing the Earth of some of its spin. Its angular momentum is being reduced, and the angular momentum of the Moon is increasing. So the total is still the same, but in effect, angular momentum is being transferred from the Earth to the Moon. So the Earth is slowing down, and as a result, the Moon is getting further away. So the length of the day, we're going to have to give up on this idea of leap seconds every once in a while. Leap seconds aren't going to cut it anymore. The length of the day is now 25 hours, not 24. So forget the idea of trying to keep clocks synchronized with the rotation of the Earth. Perhaps this is the time to think about decimalizing it and having 100 hours or something like that, 100 quarter hours in a day. Because the Moon is now getting further away from the Earth is slowing down and the Moon's orbit is increasing in its diameter. The Moon will soon be so far away from the Earth that it will be impossible to cover the Sun. The Moon's disk will no longer be large enough, as seen from the Earth, to cover the solar disk, and hence we will no longer, from this point onwards, have total eclipses of the Sun. In other words, we will still have annular eclipses where the Moon looks smaller in the sky and will cover part of the Sun from time to time, but it will never completely cover the Sun to allow us to see the solar corona. So for those eclipse chasers amongst you, you've got 1 billion years before it's no longer an option, okay? So get your bookings in because it's not going to be there forever. We are at a privileged time when it is possible to see solar eclipses. But for the rest of eternity, that is not going to be a possibility. Another consequence, perhaps a more serious consequence, of the Moon moving away from the Earth slowly is on this same time scale of 1 billion years or so, the Moon will not only be so far away it can't eclipse the Sun, but more importantly, the Moon has a stabilizing influence on the tilt of the Earth. The tilt of the Earth, the angle between the axis of the Earth and the perpendicular to the ecliptic, the plane in which the Earth orbits the Sun, that tilt of 23 degrees hasn't changed much in recorded history. We can tell by looking again through geological records. We think the tilt of the Earth has been about 23.5 degrees, give or take a degree. And that little cartoon on the left shows you what a change of 1 degree looks like. It's a tiny, you can hardly see the Earth waggling backwards and forwards between about 22.5 and 24.5 degrees. So that means the seasons have always been pretty much the same, in the sense that the seasons, of course, are dominated by the tilt of the Earth, and when the Earth is tilted towards the sun, we get a local summer. When away from the sun, we get a local winter. But if the moon is too far away from the Earth, it's difficult for the moon to actually lock that Earth into a particular axis. If the moon gets further away than about 25% more than the distance we're talking about now, then the tilt of the Earth could change not just by a degree or two, it could be wildly erratic. The Earth could decide to start spinning upside down or start spinning sideways. If the moon is not stabilizing it, the tilt of the Earth, and hence the seasons that result as the Earth goes around the sun, will become absolutely wildly erratic. So the climate will be impossible to predict once the moon starts drifting away from the Earth on a time scale of about 1 billion years or so. Other things are happening. Voyager is bombing its way out of the solar system and has been for quite a few years now. Remember, it might only take 10,000 years or so to pass the nearest star. So after 1 billion years, Voyager has passed through tens or hundreds of thousands of solar systems on its way through the galaxy. And it is carrying a gold disk, which has recorded sounds and images of Earth. And it is thought that the gold disk will probably survive 1 billion years. It's a bit difficult to be absolutely precise, but because our understanding of metallurgy, basically, we believe that the disk itself should be good for 1 billion years. So again, Voyager is going out of the solar system, and if it is caught by any of the stars on the way, any of those 10 to 100,000 solar systems that it's going to go plowing through, if any of them have life and they see this object coming through, they will be able to pick this up. The catch is that the record will survive 1 billion years. The catch is, the reason it's going to survive is because it's behind a cover. The cover is going to get very pitted, but it's going to protect the disk. The downside is the cover's got the instructions on it. So the disc that covers the record is aluminium plated with there's some uranium on the top. Why uranium? Because it's radioactive and you can trace the decay. So if any intelligent species pick this up, they will know about the decay of uranium, and they'll be able to tell how many hundreds of millions of years this thing has been drifting through space. But it will be so pitted after 1 billion years that the instructions, you spin it at this speed, and then you use this stylus in this groove, and then you get these sounds. Unfortunately, they'll have to figure that out for themselves because they won't be able to read the instructions. But hopefully after 1 billion years, the disk itself will still be readable. But of course, for us, in 1 billion years, we are going to have a few problems. In 1 billion years, the sun is going to start changing. It won't be a red giant just yet, but its luminosity will start to change. The sun is moving towards its red giant phase. And as it does so, its luminosity is going to slowly increase. It'll increase by 10% or so for every billion years. So not particularly fast. Year on year on year, it's not going to change much. But over billions of years, it's going to be noticeable that the sun gets hotter and hotter, and of course, that's going to warm up the Earth. And it will drive the Earth into a greenhouse state. And so after a few billion years, the surface temperature of the Earth is going to be a balmy 80 Celsius. We, of course, are now trying to stop global warming at the level of 1 degree or 1.5 degrees. But by this time, there's going to be no human ability to control climate change. It is definitely going to be rather warm. And we're going to have to decide whether we try and hunker down or find somewhere else to live. So the sun is going to expand into a red giant. And as it does so, the surface of the sun is going to get closer and closer to the Earth. Now, you look at that and you think, that might be a problem. even if this is only 3,000 Kelvin, a little bit cooler than the current surface temperature of the sun, if the sun expands to the point where its surface engulfs the Earth, then of course we are in trouble. But the jury isn't quite out on that one. The Earth won't necessarily be engulfed by the sun. It's often said that the sun is going to expand as a red giant, and the red giant is going to get so big it's going to be bigger than the orbit of the Earth. That's probably true. But what is sometimes forgotten is that as the sun starts to expand, the solar wind blowing off the surface of the sun is going to increase, and the sun is going to lose mass as it does so. Over the billions of years of its expansion, it will be losing mass. And if the sun loses mass, its gravitational pull on the Earth is going to decrease, and the Earth will end up moving away from the sun. So in this little cartoon, as the sun gets larger, the Earth will actually move away from the sun. So yes, the sun is going to engulf the orbit of the Earth, probably based on our understanding of its mass. The sun will end up bigger than the original orbit of the Earth, but by the time it gets there, the Earth won't be there anymore. The Earth will be a little bit further away. Some people disagree. Some people say, yeah, but if you take this into account as well, then maybe it'll still get engulfed. So we don't actually know whether the Earth is going to be engulfed by the sun or not. The Earth might survive. And for the benefit of this talk, let's just assume it does for a little while longer. After the sun has expanded up to a red giant, it then sloughs off its outer layers, and the core of the sun becomes what we call a white dwarf. This is what a white dwarf might look like. We don't really know, but it's made mainly of carbon, and the central region might be solid carbon. It might be under quite high pressure, so maybe the core of a white dwarf is actually a big diamond. We don't actually know because we can't go to a white dwarf and drill into it to find out what it's made of. But on a timescale of quite a few billions of years, after the sun has gone through its red giant phase, that's what our sun is going to end up as. But even if we survive the red giant phase, we're in trouble because the Earth is going to lose its magnetic field. The Earth's core is hot, not because of the sun. The Earth's core is hot because of radioactive elements generating heat, and they've been doing that for the last 4.5 billion years and will continue to do that for quite a few billion years. But eventually, the radiation at the core of the Earth is going to drop away, and as soon as the core of the Earth gets cold, it's no longer a molten globe of rock, it's no longer a dynamo, it no longer generates a magnetic field. So when the core of the Earth cools, the Earth will lose its magnetic field, and hence it will lose its protection against radiation. Perhaps not so much from the sun, but it will lose protection from radiation from the rest of the cosmos. Cosmic rays are going to rain down on the planet because of the loss of a magnetic field. It's thought that this is probably what happened to Mars. Mars is smaller than the Earth. It would have cooled down more quickly, so Mars lost its magnetic field a long time ago. And when Mars lost its magnetic field, it lost its protection, and the radiation from the sun might well have just stripped the atmosphere. So Mars has not got much of an atmosphere, at least in part, because it hasn't got a magnetic field. And that's partly in part because it's a smaller object. So we are going to lose our magnetic field and lose our protection. So if we survive the sun going through red giant, then we're going to be pulverized by cosmic rays. And if that wasn't enough, what else is around the corner? We're going to crash with Andromeda. Yes, the Andromeda galaxy is going to come hurtling in on about the same time scale. Now, although that sounds even more cataclysmic, actually it isn't, because galaxies do collide with each other, and the Andromeda galaxy is going to be a fantastic astrophotography opportunity as it comes towards us. You'll no longer need a telephoto lens. You'll need a wide angle, then a super wide angle as it gets closer and closer. And as the two galaxies pass through each other, there's going to be a riot of new star formation as these two galaxies pass through each other. And then the Andromeda galaxy will pass through the other side, and then gradually they will settle down into one mega galaxy, whose name might be Milkdromeda or something else. I'm not sure. We've got plenty of time to decide what the name is. We've got 5 billion years to decide what we do. It's unlikely that stars are going to collide with each other. even if you take hundreds of billions of stars in one galaxy and hundreds of billions of stars in the other galaxy and let them pass through each other, no two stars are probably going to collide with each other. All of the gas is going to get churned up and you're going to have huge tidal effects, but it's unlikely, for instance, that the Sun or the Earth get hit by another star in the Andromeda galaxy. So probably two galaxies passing through each other will not be a cataclysmic event. If the Earth survives the Sun going through Red Giant, it will probably survive Andromeda galaxy colliding. If the Sun gets pulled out of the Milky Way, the Earth will simply go with it because it will be a relatively slow process. Look at the times here, 4 billion years, 5 billion years. If the Sun gets pulled out of the galaxy, it'll happen over hundreds of millions of years and the Earth will simply go with it. So that is not the end of everything. That's just an interesting punctuation mark in the Earth's history. At 10 to the 11 years, we're now talking, what, 100 million, 100 billion years into the future, the slowdown of the Earth because of the tidal effects of the Moon now come to their conclusion. Now the two are locked together. One day is the same as 1 month. In other words, the length of time it takes the Earth to spin once on its axis is the same as the length of time it takes the Moon to go around the Earth. They are both the same length of time. So not only does the Moon present the same face to the Earth, which it's always done, it has done for a long time, the Earth is also tidally locked to the Moon. In other words, one side of the Earth is always facing the Moon, as well as one side of the Moon is always facing the Earth. So, in other words, the Earth now mirrors what the Moon has been doing for a long time. So we're used to the fact that we always see the same face of the Moon. We never see the far side, we only see the near side. Well, the same will be true the other way around. The Moon will only see one side of the Earth. Or if you turn that around, people on one side of the Earth will always have the Moon in their sky, and people on the other side of the Earth will never have the Moon in their sky, because they will be tidally locked and always going round lockstep, a bit like Pluto and Charon do at the moment. And for those of you who think that's an interesting Photoshop picture, no, that's a real picture of the Earth, and that's the far side of the Moon, which is why you don't normally see that, and it was taken by Deep Space Climate Observatory from obviously a vantage point a long way from the Moon. But it gives you a nice indication of the relative sizes of the two objects. It looks like it's been photoshopped, but that is a genuine photo from a deep space probe. We're now at 10 to the 12. The red box has reached the right-hand edge. We are now 1 trillion years into the future. And this is the environment of the Milky Way, the so-called local group. If we have a look, we see the Milky Way is a big galaxy, and there's lots of tiny galaxies all around it, little satellite galaxies, some of which you've heard of, like the Large and Small Magellanic Clouds, but there's loads of other dwarf galaxies there as well. And we've already said that the Milky Way is going to collide with the Andromeda galaxy, and ultimately it'll pull in M33 as well. But on these timescales of 1 trillion years, everything in the local group will be swallowed up into one mega galaxy. We know that galaxies are cannibals. That's how they grow. That's how they evolve. Galaxies eat each other. And usually, big galaxies eat small galaxies. We don't see it happening at the moment, but on the future timescales we're talking about, the Milky Way, or the Milky Way and Andromeda, are going to hoover up everything in our neighborhood. But what about galaxies further away than the ones right next door to us, like Andromeda and M33? Well, it is possible now, and it will be possible in the future, to see galaxies, even those, because of the expansion of the universe, that are receding from us faster than the speed of light. So, for instance, even now, or as of September 2020, we know it's possible. We can photograph a galaxy, for instance, receding from us at twice the speed of light. We can't see all the galaxies in the universe. We can only see galaxies in the universe in our so-called bubble of the observable universe. That effectively just defines the limit of those galaxies that we can see. And we know there are lots of them in the observable universe because the Hubble deep field or ultra deep field or extreme deep field, pointing in various directions at the sky, show us thousands upon thousands of galaxies in a tiny patch of sky, and it would be the same regardless of which way we looked. So by extrapolation, we can work out there are hundreds of billions, if not trillions, of galaxies out there. But there will come a time, on this time scale of 10 to the 12 or so, where the universe has expanded so much that even the closest galaxies will be beyond our ability to see. And the equivalent of a Hubble Deep Field won't look like that. The Hubble Deep Field, instead of showing galaxies and a few stars, will basically just show the stars. In other words, those are two stars in our Milky Way that the Hubble has picked up, but we will not be able to see in the future any galaxies beyond our own Milky Way. And it's rather humbling to think that if a civilization comes to be in 1 trillion years' time, if they build themselves the most sophisticated telescope they can, Hubble Mark II, and they point into the universe and ask themselves, I wonder what's out there, if they take the longest exposure they care to take, they will see nothing other than the stars in their own galaxy, because the universe will have expanded so much it will be physically impossible for them to do so. Doesn't matter how technologically advanced they are, doesn't matter how good their telescope is, they will only see whatever is in their own galaxy. They will think the entire universe is simply their own galaxy, because they will have no idea that there are other galaxies out there expanding away at enormous velocities. We know that now because we know we can see those galaxies, but eventually that will be impossible. So future civilizations might come to a completely different conclusion about what the universe is and their place within it. The hydrogen that was made in the first 3 minutes, the beginning of everything, all of the protons and neutrons that make all the hydrogen, makes helium as well, but it's the hydrogen that fuels stars. For reasons I'm not going to go into, stars don't start by burning helium. They start by burning hydrogen. They might then make helium, and then they might make carbon and other things. But everything starts by fusing hydrogen. It took 3 minutes to make all the hydrogen in the universe. But after 1 trillion years, red box on the right-hand side, it's nearly all gone. And if all the hydrogen has been used up, that would imply there's no new star formation. As a little bit of an aside, a hypothesis, not proven, but a hypothesis is, well, maybe it'll be possible to actually build some stars out of heavier stuff. Maybe it's possible, and this is just the result of a simulation, not any observation, maybe we can make stars by starting with heavier elements. Maybe it's actually possible to get heavy elements together such that you can have a nuclear fusion reaction in the core of a star, but the outside temperature will be so low, it could be not thousands of Kelvin, it could only be hundreds of Kelvin. It might actually be lower than the ice point. It is physically possible, we believe, to make stars in which there are nuclear reactions at the core, but the star itself is frozen. Ice in the surface of the star. And when I say frozen stars, I don't mean Disney. I don't mean that particular frozen star. If that's the picture you've got in your head, just let it go. Because what I'm talking about is nuclear reactions in the core of a star, but conceivably water ice in the outer part of the star. The idea of a star being frozen is pretty amazing, but it is only a hypothesis. As far as we know, you need hydrogen to make stars. And this is not the end of the story. 1 trillion years into the future is not the end. Before going any further, and yes, I'm not quite done yet, before going any further, we just have to remind ourselves what's going to happen to the universe in general in terms of its expansion. Sorry for the graph, but for those that like colors, I've tried to make it as colorful as possible. How big is the universe versus time? So that's where we are now, and the size of the universe is 1. Let's take 1 as just, I don't know, the distance between us and the Virgo cluster or something. It doesn't matter what the scale is, it's just a relative scale. So that's how big the universe is, and it was smaller in the past, and at some point it was 0 size, and that's what we call the Big Bang. Notice that the the age of the universe depends on which of these colored lines we're talking about. Each colored line corresponds to how much stuff is there in the universe. If we don't know how much stuff there is in the universe, then we don't know how old the universe is, and we don't know what's going to happen in the future. For instance, if the universe had a huge amount of stuff in it, a lot of mass, then gravity would take hold and it would expand, and we would follow the orange curve. It would get bigger, but eventually it would start getting smaller again. In other words, if there's lots of mass in the universe, the Big Bang would have made everything expand, but eventually gravity would win because there's so much mass, gravity is going to be strong. And eventually the expansion of the universe will stop, and then it will all collapse, and we'll end up with a big crunch billions of years in the future. That's a so-called closed universe. But we don't think that color is the one we're on. We think at the moment our best guess, when we look out into the universe and ask how much stuff is out there, we think the best guess is there's that much mass and that much energy, and we think we're on the red line. Notice they're all very close to each other, so it's very difficult to tell now, but we think we're on the red line, and the red line, notice, means the size of the universe gets larger and larger and larger and larger as time goes further and further into the future. Not only does it expand, but notice the gradient is getting larger and larger and larger. So it's expanding, it looks like it'll never stop, and it's accelerating. Not only is it expanding, it's expanding faster every day. So that's the red line, which is the line we think we're on. So as far as we know at the present, the universe is eternal. There's no indication that the universe will come to an end. There's no indication that the universe will run backwards and will end up with a big crunch. Still possible, but the evidence doesn't point that way. So that's why I showed this graph, just to make it clear that we're just going to assume the universe goes on forever. And notice the numbers are now getting really silly. I've replaced that top line from sort of 0 to 12. I've now started at 12, and we're going up, not 10 times further into the future for each box. We're now 1,000,000 times further into the future for each box. So we're talking about a zillion years, or a gazillion years, or I don't know what the labels we give to these things. We're going to give up on millions and billions and trillions. We're just going to talk about 10 to the power what? How many zeros after the 1 do we need to give us this particular number? So where did we get to before we had this aside that the universe is going to go on forever? I said it took 3 minutes to make all the hydrogen, but the hydrogen is starting to run out. And we don't think we can make stars out of anything else from hydrogen, anything else other than hydrogen. So if there's no hydrogen left, stars might live for an awfully long time. Some stars might live for trillions of years. But the lifetime of any star is not infinite. So what does that mean? There will come a time when there were no more stars shining. They may have lasted many trillions of years, but once the hydrogen has run out, no more stars can be made. Even if stars last for a few trillion years, there will come a time when the last star has winked out. This is called the age of starlight, or in this case, the end of the age of starlight. The stars will still be there, or at least the stuff of the stars will still be there. They just simply can't fuse to make energy to shine. So there will be lots of dead stars floating around, like zombies in the galaxy. There will be lots of white dwarfs like our sun at the end of its life. There will be lots of neutron stars. There will be lots of black holes, none of which will be shining in the sense that they won't be fusing hydrogen or any other elements to make the stars shine. White dwarfs are only called white dwarfs because they start hot. They aren't generating energy in the sense that other stars are. They're simply born hot, and they will simply cool down. So our sun might start as a white dwarf once it's gone through the red giant phase, but that's just because it's hot and it's going to sit there and cool off, and eventually it's going to become a black dwarf. And if you can't see that very clearly, make it a bit brighter, but okay, it's a lump of carbon. No matter what you do, it's going to be a large black sphere. And given enough time, and we're now talking about many trillions of years into the future, basically even white dwarfs will just end up as dark objects. Some stars, for reasons I'm not going to go into the detail, some stars are going to get thrown out of the galaxy, and a whole load of stars are going to get eaten by the supermassive black hole at the center of our galaxy, and presumably the center of all the other galaxies out there. So basically, black holes are going to gobble up everything else. And the mechanism by which they do that has been mapped out recently. A distant galaxy has been mapped by SOFIA. SOFIA is the Stratospheric Observatory for Infrared Astronomy. It's a big infrared telescope in the back of a 747. Recently decommissioned, I'm sad to say. They're no longer flying this as of, I think, a few months ago. But this particular observation of a galaxy mapped out the direction of the magnetic fields, and it's thought that matter flows along these magnetic field lines and, in a sense, gets funneled into the supermassive black hole, which is sitting right at the center of this particular galaxy. So once all the stars have finished shining, stopped shining, and all the fuel has run out, some will be lost into intergalactic space, and the rest will be eaten by simply flowing along these magnetic field lines. We're not absolutely sure what's going to happen to all the atoms in the universe. An atom is made of a positive charge in the nucleus and lots of negative charged electrons buzzing around, and the particle in the center of the nucleus there responsible for the positive charge is called a proton. Protons are part of every atomic nucleus in the entire universe. And we don't know if protons decay. We don't know if they change or whether they will always be protons. If protons decay, then every atom in the universe will fall to pieces, because you can't make an atom without a positive nucleus and a negative electron buzzing around it. Now, we don't know if and when this is going to happen, because we can't easily do the calculation that says whether this is likely to happen or not. It is not going to happen before this time up here. Protons are not going to decay before a time period of order 10 to the power 36, a million years into the future. But they may decay after that point. Let's assume they don't, just for the time being. Even if protons don't decay, then atoms still won't last forever. Because, for instance, the only atoms in the universe are in these black dwarfs. You don't have atoms in neutron stars. You don't have atoms in black holes. The only atoms that exist will be in these black dwarfs, and eventually they will evaporate through a process I'm not going to describe in detail. So there will come a time, 10 to the 42 years into the future, where there are no atoms at all in the universe. Black holes will continue to exist for a while. Black holes at the centers of galaxies, if galaxies are merging with each other, the black holes are going to grow. Black holes will not be millions of solar masses. They will not even be billions of solar masses. They will continue to grow until they are probably trillions of solar masses in each of the black holes because of the accumulation effect of galaxies merging with each other. But even black holes are not eternal. They will not last forever. They evaporate. To the best of our knowledge, we haven't been around long enough to check this, but to the best of our knowledge, black holes evaporate, providing that you wait for a really, really, really long time. So why do black holes evaporate? Well, it's a quantum mechanical process. Quantum mechanics is a theory which, as far as we know, has stood the test of time for 100 years or so. Quantum mechanics tells us that you are allowed to borrow energy from nothing and make matter and antimatter. You can basically just borrow it from nothing, make some stuff, but then the matter and antimatter will annihilate with each other to generate energy with which you pay back the loan. Sounds like a bit of an odd thing, but that's the way particle physics works. You have energy, you make stuff, they annihilate, you get your energy back again. That's happening all the time. Borrow energy, make stuff, stuff annihilates back to energy, back and forth, back and forth. What's that got to do with black holes? Well, it is hypothesized by Hawking et al. That if you actually have close to the surface of a black hole, nothing can get out from the inside, but if you have a process very close to the surface of the event horizon, the watershed point at which you can't escape from a black hole. If you borrow energy and make two things, and one of them falls into the black hole and the other one doesn't, which could happen, then to all the world it looks like the black hole has just emitted this thing, because it can't annihilate with the other one, which has fallen inside the black hole. So it's as if something has got out of the black hole. It's not coming from the inside, it's coming from right outside the event horizon, right outside the surface of the black hole. So it's not breaking any laws of physics, but because it looks like the black hole is radiating something, this has now become known as Hawking radiation. Hawking was the first one to propose this is a mechanism by which black holes will radiate energy and hence lose mass. It's been calculated that the radiation increases with smaller mass. So large black holes don't radiate much. Tiny black holes radiate a huge amount. So that means that during a course of its life, a black hole will evaporate and the radiation levels will increase because it's getting smaller and the radiation levels are going up, and it will disappear in a flash of radiation at the end of its life. Even supermassive black holes, although they radiate less, they will still eventually evaporate. It'll just take them a huge length of time to do that. Supermassive black holes will eventually radiate all of their energy away and will evaporate to nothing, but it will take trillions of times longer. So in other words, all matter in the universe is going to end up as basically turned to radiation. All the mass of a black hole, the black hole itself will disappear, and all you'll end up with is the radiation from those black holes. It'll probably end up as radio waves. Not very energetic gamma rays, not very energetic light, not very energetic infrared. Because the universe is still expanding, all of this radiation is getting stretched out and out and out and out. So everything will just end up as very, very, very low energy radiation, radio waves. So is this the end of time? Have we reached the end of the talk? Well, very nearly, yes. 10 to the power 100, which is off the end of this particular timeline up here, no red box anymore. 10 to the power 100 is called a googol. Not that one. Google in color is simply a misspelling of the actual Google. I think somebody thought that they were setting up a company that was this, but they actually spelt it wrong and got that. So Google is 10 to the power 100. And after a Google years, it is thought that there are no more black holes, everything has turned to energy, and that energy is simply cooling off as the universe expands. The so-called heat death of the universe. After this point, nothing happens. There's no more matter left in the universe. There's just a bit of radiation floating around, and that radiation is getting more and more and more stretched as the universe continues to expand. So time becomes, well, if nothing is happening, time becomes effectively meaningless. And just to put it into perspective, I don't normally do this with 10 to the power large numbers, but let me just remind you what that actually means. That is a googol. It is 10 million, oh, you can do it yourself. Okay, it's a very large number, but it's still possible to calculate the physics of what's going to happen on those time scales and calculate that it's going to take roughly that long for the last black hole to evaporate. Obviously a little bit of guesswork in there, but the time scale is about right. And beyond a googol is not eternity. It's a big number, but it's not eternity. Eternity is much bigger than that number, remember? Which is why you get quotes like this one from Woody Allen. Eternity is a very long time, especially towards the end. But another way of putting it into a little bit of perspective is to take the XKCD approach and think about humans on a time scale of a googol years. A human is a system for converting dust billions of years ago into dust billions of years from now via a roundabout process, which involves checking email quite a lot. So that's basically a human perspective on the whole story, if you like. So let me finish with an epilogue. I don't want you all to go away too depressed this evening, so let me put a slightly different spin on this. Yes, everything is going to come to an end eventually. That's inevitable. But at the moment, we live in a golden age. The sun is middle-aged and well-behaved. It's been well-behaved for billions of years, and it's going to be good for a few more billion years. The moon is at just the right distance to stabilize the Earth's axis tilt and hence stabilize our seasons. And it also, as a byproduct, gives us the spectacle of a total eclipse of the sun. Thanks to evolution, we are in a position to explore and discover and understand the universe in which we live. We can visit our closest neighbors by sending probes, and we can build ourselves, with a bit of ingenuity, we can build ourselves telescopes that allow us to see galaxies billions of light years away. And hence we get a good idea of the universe in which we live. But mankind couldn't have done this a long time ago. Mankind could not have existed in the very early universe because we needed generations of stars to make the heavy elements. We needed lots of stars to take hydrogen and make helium, and then we needed more stars to take the helium and make carbon and nitrogen and oxygen and calcium and phosphorus and all the other elements that make us who we are. So we had to have lots of generations of stars running sequentially to make the heavy elements to make us. And mankind could not exist in the very far future. We've just seen that the very, very far future is really dark and really boring. So you could argue the best time to exist is now. Thank you all very much.